In this video, I will show you how to find the net magnetic field when you have current distributions that are not just one straight wire or one circular loop or just a solenoid. So I have shown you expressions for the magnetic field from a single straight wire. There are, in general, the approach that you will take to find the net magnetic field. You will have to use the superposition principle, and you can use it in this case. You need to use it, and you will find the net magnetic field from somewhat arbitrary current distributions by splitting them into pieces and then finding the magnetic field from each one of them, and then you will need to add all magnetic fields together to get the net. Okay, so to find B net, you will need to use the principle of superposition. And I will show you some examples for how you can do that. Let's say we got one straight wire, and you probably can see by the way that I'm making this how you will divide it into pieces. Now, let's say we have a current. Conventional current is flowing this way on this rectangular wire. We know how to find the magnetic field from a straight wire. Let's say I can place the observation location wherever. So I could put the observation location here. I could place it outside. No, I cannot place it outside. I don't have something like this. It will have to be, so the constraint that I have, if I want you to use the expression I found, my observation location always needs to be closest to the midpoint of the different pieces. So I can place it here, and I guess that is it. Or I could also move the observation location. I could move it on the z-axis if I choose. If this is the x and this is the y, and if I make the z direction pointing out of the page, I could move my observation location on the z-axis, and then the observation location would be from the observation location to the midpoint of each wire. That line would be perpendicular to the wire, so you would be able to use the expression that I showed you. In any case, so when you have something like this, you would divide this rectangular wire into pieces, and then you would say for B net, you would find the first magnetic field, and then you would add the second one, and then you would add the third one, and then you would add the fourth one. Okay, that's how you will find the net magnetic field at the center of this rectangular wire. Now, you can do something similar. Let's say if I have a circular loop or two circular loops. So now I'm gonna show you the side view. Okay, so let's make this one loop, and let's say I have another loop here. Now this is the side view, and let's make the current. So this is the side view. If I show you what the top view looks like, so it's gonna look something like this. But because I will have the centers of the two circular loops of being coaxial, they overlap essentially the two circular loops. You only see one if you look at it from the top. Let's make the current flow this way, and let's say this is circular loop 1, this is circular loop 2, and I want to find the magnetic field here in the middle. Then similar approach, you will do the net magnetic field at the observation location is B1 plus B2, and then to find B1 you would be using the expression for the magnetic field for a single loop, and to find B2 you would do the same thing. You would be using the expression for the magnetic field from a single circular loop, and then you would add the two magnetic fields together. Do pay attention though, because the net magnetic field is a vector. Okay, the equations that you have for the magnetic field from a straight wire, from a loop, and so on, for a solenoid, those expressions will give you just the magnitude. Now, it is important to use the expressions to find the magnitudes of B1 and B2, but then you have to use your intuition and your knowledge about Biot-Savart's law to be able to write the 3D vector for B1 and B2, and then when you add B1 and B2, make sure you add the vectors in order to find the net magnetic field. Okay, you cannot just add numbers like the magnitudes that you get for B1 and B2. You have to do the calculation for the net magnetic field using vectors. Now, I do want to give you an example for and also mention something in particular. Let's say, so if we have a current carrying wire here and another one here, and then I am going to connect those two with a semi-circular loop, and we have, say we have a current. So we got a current going on, this is I, and then it goes this way, and then of course it goes that way. What we will do, as before, we can divide this into pieces 1, 2, and 3, and then of course I can write B net as the sum of B1 plus B2 plus B3. Now, if I place my observation location here at the center of the loop, pay attention to what happens to B1 and B3. I know for a short wire, magnetic field is the mu naught over 4 pi I delta L cross r hat over r squared. Right, now remember that delta L points in the direction of conventional current. This means, let's say for wire 1, I got my, let's say 1 delta L. Okay, this is one particular delta L here. Now, the vector R goes from the source to the observation location. The observation location is here, the source is here. The vector R is this one. And of course, the unit vector R hat will point in the same direction as vector R. But here is an interesting fact about cross products. If this is delta L, and this is also the direction of R hat, when you find the cross product, you will find that to be exactly 0. The magnitude of the cross product depends on the sign of the angle theta between the two vectors. And when those two point in the same direction, this cross product gives you exactly 0. What this means, if you plug in a 0 for the cross product, you get a 0 for the magnetic field. If you add all the contributions to the net magnetic field here at the observation location from wire 1, you will get exactly 0, because for all of them, r hat and delta L point in the same direction. For all of them, the cross product will give you 0. Now, this means B1 is exactly 0. For wire 3, the vector delta L points in the direction of the conventional current, so my delta L will go to the right. The vector R goes from the source, which is here, to the observation location, which is here. So the vector R points straight to the left, which means the vector R hat will also point straight to the left. When your delta L goes to the right and your R hat goes to the left, you got an angle of 180, and we know the sine of 180 degrees is also 0, which means delta L cross R hat gives you 0. Similar reason, a 0 here will give you 0B. This means this straight wire creates no magnetic field at that observation location. That means B3 is 0. Now, what I want you to do is to remember this. Well, one thing, remember the approach. Always, you will need to break your current distribution into pieces. You will need to add the contributions to B net from all of those pieces. However, and when you do that, you need to be careful to make sure you find out the directions of the magnetic fields using Biot-Savart's law. But if you have a case where you want to find the magnetic field, say this is a straight wire and you want to find the magnetic field here, you will not have to worry about the contribution of that piece to the magnetic field. This is the reasoning. Make sure you remember it and use it to prove that this and this piece of current, they don't contribute anything to the net magnetic field, at least at that observation location. Do remember that yes, these two current carrying wires, they do create a magnetic field everywhere around them, like here, but not ahead and not in the back. So if the charges are moving to the right, they create no magnetic field along this line, and they create no magnetic field behind them over here. And the same thing is true for this piece of wire.